what we did in the past 20 years or so. So basically, my interest is playing with light, manipulate light, and structure them as much as we want. We could put a quote there arbitrarily, but we are not there yet. But I'd like to share you what people have done in the past 20 years in terms of space and time sculpturing of light. And you see that towards the end, it's related to some of the topology problems we're interested in here. Okay. It's not moving. Okay. So here's the outline of the talk. I first will give an introduction of the background. Then about 1/3 of the talk will be on how we structure light in spatial domain. And some of the topics you already seen in the previous speakers. And I will show you mainly the result in the past 20 years and some of the applications. And you see that a lot of the work I talked yesterday is kind of abstract. We don't know the applications, but if you look back the history, some of the stuff we did 20 years ago, I faced the same question. Whenever I give a talk at the conferences, people ask, what's the application of this? And my answer would be, I don't know. But hopefully later on, there will be applications. But indeed, there are applications coming up. So my hope is that for this spatiotemporal stuff we did recently, we also find applications in the near future. So I will start with a video from the internet. This video is about a phenomenon called the toroidal vortex or vortex rings. So you have seen that in a daily life. Let me make the sounds lower. So this is a phenomenon in fluids I think you guys are very familiar with. And in fact, if you have people smoke rings coming out, it has these topological structures. Or if you go to an aquarium, if you look at some of the dolphins or beluga whales, and they like to play this kind of things just like smoke ring, but in air bubbles underwater. You will see that they can create these type of knots, ring structures. Actually, it's not knots yet. But it's a lot of fun for those animals. And but the question is, other than fluidics, can we create such a structure with light? So that's the beginning of our pursuit. And in the end, you will see that indeed we can do this with light and probably much more with light. So this video is a little bit long. I can move a little bit faster. As you can see, a lot of interesting phenomena from nature has this type of topology. And yeah, that's a whale. And I think next is actually a volcano. And the volcano also puff up the smoke rings, this kind of structure. And so with that question in mind, so this is kind of a structure, topological structure is now daily life around us. I want to mention one other thing. I think yesterday we also have a speaker, probably Lutz, mentioned this. This is a paper by William Thomson in 1867. So at that time, he was trying to use these structures, knots, toroidal rings, to explain the atomic structure, what they should look like. And here's, you have seen a lot of this already from this winter school. So basically, he's trying to say, well, the atoms, so for example, hydrogen would have this ring structures, just like the rings that the dolphins was playing. And there are some other knotted structures for different elements of carbon, oxygen, etc. Of course, we know it's not right. It's wrong. So basically, it's saying that vertex theory of the atom is only a dream. It's self-unproven, can prove nothing, and any speculation from the opponent are mere dreams about dreams. So that was many years ago, okay? But whether the conclusion is true, I know with quantum mechanics, and we know the atom does not have this kind of structure, right? But all the theory developed actually may be useful. I don't know. I mean, with the institute here, we might be able to build a matter with this topology, and you're probably going to have very interesting properties. So we don't have the nature atom with this kind of a structure, but we can have a man-made atom with this structure and probably have some interesting properties. So anyway, that's kind of like a background of why we are interested in this kind of things. In light, we want to produce this topology. But you can see that also from yesterday's tutorial. If you want to build this topology, actually, you need to have a lot of degree of freedom. So you need to be able to control the parameters very precisely, spatial and orientation, and etc. So that means we need to be able to control the light or structure the light. So that's actually what we did. Not only just us, actually, the community was interested in this in the past 30 years or so. Now, here's actually the kind of a conceptual diagram. We know light is electromagnetic waves. It has different parameters. For example, it has a different color or wavelengths. It can have different intensity, bright or dark, what called amplitude. It has a polarization, so electrical field have a different orientation of oscillation. And it also has a phase. So those are the main parameters of light. And for optics person like me, in the past, we have been dealing with these parameters, of course, but there's two main categories of those businesses. One is to dealing with those parameters in space. So we define this function in the domain of a spatial domain, it's the X, Y, Z, etc., right? And this is actually something you're very familiar with. You're seeing this daily life. This is basically like a kid's drawing a picture. So you have a piece of paper or canvas, a different location, you have a different intensity, different color. And of course, there are some parameters like polarization of phase. We don't see that directly with our eyes, but you can imagine that this is something that you can do. It's actually spatially control of light or spatial extraction of light is just an imaging problem. Okay. But physics, we know that there's a space and also there's a time. Diagonal directions, if you do that same thing, is something also in optics we are very familiar with as a communication problem. So you have this different degree of freedom, so different parameters, you encode it in time, and you send it out to the other side, you decode it, you have information transferred. That's a communication problem. So we say this is the information hidden in photon, but we define it is in space or time. But I use all here because in the past, these two communities actually, we don't talk to each other. We use a similar language, but we don't understand each other. Actually, the communication guys and the imaging processing guys, we don't talk to each other. So the second half of the talk will be, can we combine it together? But the communication problem, we don't do a lot of here in my group. We mainly deal with the spatial structure of light. With that, this is actually another slide showing what happens in the field. If you have a electromagnetic wave, for example, light, we write down these parameters. So this is the electrical field, X, Y, Z, and T. Typically, we try to make things simplified. Okay, what we did in textbook, we're going to separate those into different components. This is the amplitude. This is the phase. This is the polarization. Polarization, of course, has two components. And then this is the spatial part, and then there's temporal part. They're separated. But like I said, the communication guys, they dealing with this part. The imaging processing guys is dealing with this guy. And we don't talk to each other that much. The reason is actually very simple. When the space and time are coupled together, things are getting much more complicated. So typically in the past, what people try to do is actually to decouple the space and time. And if you look at a textbook, these are the things we're familiar with: the Gaussian beams, a spherical wavefront, spatially homogeneous polarization states for like X polarization, Y polarization, circular polarization, etc. Or you have, continuous wave Gaussian beams or pulsed Gaussian beams. That's what typically would be deal with in a textbook. But what happened in the past 20 or 30 years or so, there's a trend. The trend is that we're taking this carrier frequency, omega 0, and the direction of propagation, but then the rest of the stuff was lumped into a big packet. And that packet has a certain structure in it, and that's related to the topology. So, of course, this is not happening overnight. It had take a long time, so there's different steps in between. For example, initially, we tried to make the amplitude part more complicated. You see interest of these donut beams or bottle beams, and we try to make the phase more complicated. Instead of a spherical wavefront or plane wavefront, we start to look into this so-called vortexes or orbital angular momentum states of the light. So the phase structure has this helical phase structure. And for me, actually, I started this research in the polarization part. Instead of having these spatially homogeneous polarization states, what if I can intentionally structure the polarization? For example, this is what we call cylindrical vector beams. And also for the temporal part and the spatial temporal coupling part, that's what we did in the past 5 years also. We were able to create this so-called spatial temporal optical vertices. This is the toroidal rings that I just showed you from the dolphin, but in light. And at the same time, there's another group from Southampton has this polarization topology similar to the toroidal rings, but it has the polarization kind of distributions. And this is the hot films we produce later with light by just twisting the face of this toroidal vertexes. So that's basically the trend in the past 30 years also. But let me just go back and look at the space part, what people have been done. So this is just like an overview, see what's the important achievement. One of the important achievement, of course, we have heard already is the OEM of light, orbital angular momentum, with these optical vertices. And there's a lot of research that goes all the way back in the early 90s. But now there's actually certain applications. The main applications now people are pursuing is in the communication. So basically, you can encode information with the topological charge of the phase front. And in principle, the quantum numbers of the topological charge is infinite. So it's from minus infinity to plus infinity. If you can jam those information through the same optical channel, you can imagine that you can increase your communication link capacity dramatically. And indeed, this is actually the first demonstration in 2013 in science. At that time, the demonstration is 1 terabits per second transmission rate of signal through a single link of fiber. And last year, the record of these type of communication link is 1,000 terabits per second. So you can imagine that for one video movie is about a couple gigabytes. Now you have 1,000 terabytes per second. You can imagine how much the bandwidth that you have with this type of system. So this is actually close to practical application now. There are people who start to deploy that with hundreds of kilometers testing link right now in southern China. And one of the things actually we will need to come back, I did not have a picture here, is when we're dealing with this OM communications, there's a key component called OM sorter. Basically, you jam all the orbital angular momentum in the same fiber. On the other hand, far away, you have to separate them. And this is actually what we call OM sorter is doing. And it uses a technology called optical conformal mapping. And I'll come back this a little bit later because we need this to form these toroidal ring structures. So that's the phase part of structure of light that actually gave us some interesting applications. For me, I start this actually from the polarization stuff. So you can see that we can structure the polarization of light with this kind of symmetry. And this kind of a polarization distribution also have a singularity similar to the vertex singularity, but that's a phase singularity. This guy's is polarization singularity. And it turns out, I didn't have time to explain this, but it turns out this type of polarization singularity and a phase singularity are linked through spins. So, okay, if you have a spin state, you decompose that into the different components in the polar coordinates, you actually end up with a spin decomposed into orbital angular states. But anyway, that's the kind of initial work that we started for spatially structured light in polarization. And again, I did not have slides to show you. For this type of polarization states, if you focus it, you will produce a topology called skymions. So this is actually linked to skymions as well. And for us at that time, we tried to find some applications of these very strange polarization states. And a very natural link at that time was to link this with the plasmonics, because plasmonic has a polarization dependence. And we're playing with the polarization of light. So if you couple the polarization distribution of light to a certain structure, they match to each other. We call it mode matching. That give you an ideal result. So I think yesterday, somebody asked me what the possible application of the toroidal, etc. And that's related to this. So if you have a nanostructure, has a certain modes in it, and for normal light, like a Gaussian modes, if you excite it, it doesn't happen because they don't match to each other. However, if you have a nanostructure that has a toroidal modes of it, and you use a toroidal light to excite it, you will be able to excite those modes very efficiently. And sometimes we call those modes are dark modes, because normally you don't have ways to access to it. But now with the capability of playing light in space and time, you will be able to access to those hidden modes or dark modes. So those are kind of things that I think is worth of exploring. This is just one example to show you that, for example, this guy over here, there's one interesting problem in the community for near-field optical scope microscopy is that can you create a very high intensity of light at confined space, and you can use that light to excite, for example, Raman spectroscopy or fluorescence spectroscopy, but with minimal background. And here is just one possibility. You can have a metal-coated, fully metal-coated probe, and you inject light from this end, and you see that there's a surface wave excited, and it goes all the way to the tip end. The tip end has this localization of the magnetic waves, electromagnetic waves. And but in order to excite this, you have to match to this mode. In this case, the matching mode is actually the radial polarization I show you in the previous slides. And here's actually a group in Israel actually demonstrate this. They fabricate this with a sharp needle integrated center And if you excited with, this is actually the symmetry axis. If you excited with the radial polarization and surface with propagate to the center and localized to tip apex, you can have a highly localized field. And before I return to Shanghai, actually, this is a lab in Dayton. We actually built a system like this and to excite the localized surface plasma and apply that for semiconductor characterization, which is to use the Raman spectroscopy to measure stress in silicon chips. And this is actually the system we built as a prototype we delivered to Fraunhofer Society in Dresden. They were working with AMD at the time to testing the capability of the system for computer chip characterization. And you probably don't realize it in your daily life. If you go to market, you want to buy this high density magnetic disk from Seagate. Actually, there's such a polarization manipulation techniques embedded in there to excite surface plasma. And also for semiconductor fabrication, some of the lithography system, there's an illumination pattern in it. Again, we don't realize it. There's an illumination pattern with these polarization states arranged symmetrically to illuminate the wafer to do the lithography. So, like I said, 20 years ago when we started this, people ask questions, what's the applications? At the time, we don't know. But gradually, there's application actually coming up. Some of them are rather important.
What wavelengths do you use usually?
What I mean?
For experiment, what wavelengths?
For our experiment, typically we use the visible light, but the principle can be extended to other wavelengths, of course. Like I said, there's a connection between the vortexes and the radial polarizations through the spin optical coupling. So we also spent some time to study that effect. A byproduct of that is that we come up with a design that is sensitive to the spin states. So in this case, if you take a circle and you cut it, you stretch it into Archimedean spiral, and that spiral turns out to be sensitive to spin states. So one of the spin states will be able to focus to the center very well, and the opposite spin will become actually second order base cell. So the center will be dark. And you can use this to differentiate the spin that's coming out to your sample. So anyway, the end result around 2012 or so, finally, we come up with this system that allow us to control all the components, so those parameters of light in transverse plane, spatially. I will not go into the detail, but basically we use two spatial light modulators. And these spatial light modulators are combined through what we call a 4F system. That's basically a relay. So this part, we control the phase. And then we image that phase to the second section of the SLAM. We play some optical tricks. We put a quarter wave plate here, basically. And it turns out by doing this, we can use this section to control the amplitude. So amplitude of each point in space, and this phase, the amplitude. And we relay that to the section 3. Again, we have a quarter wave plate here, but we don't have a polarizer after that. So this allows us to control the polarization orientation for each point spatially. And finally, the last section allows us to control ellipticity. So now if you see this with this 4 section of this SLAM, we actually will be able to control all the spatial degree of freedom of light in the cross section. And this is the system actually we have in Shanghai. It allows us to create all kinds of weird distributions of light in space. For example, different topological charge, different spin states, and amplitude, spin connections, etc. So the information I would like to convey to everybody here is that nowadays we have the capability to fully control the degree of freedom of light in one cross section. Of course, you might ask what's the use of this. So this is actually one example we pursued in the past. Let's just assume that you want to have a certain distribution of light. For example, very long skinny type of needles. So long depth of focus, but with transverse dimension diffraction limited. Okay, now how can we create this type of focus? It's very easy, actually. If you write down this distribution as a function, so basically you have E, X, Y, Z, right? That's your desired distribution of light. And you write it down, and I will change the E, the electrical field, to I, current. Okay, so become I, X, Y, Z. But then I add a oscillation component, I, Italy, I, omega t to it. So the current start to oscillate. So that's an antenna, right? And then for antenna, of course, is going to radiate. You can calculate what's the radiation pattern of the antenna in a far field. So this is a typical calculation for a long extended focus. And you see that the pattern of the light would have a different amplitude, a different phase, and different polarization distributions. But imagine that I can create this as a source. Okay, so I have this as a source for illumination, then I time reversal it. So reverse propagation direction. You will be able to create the focus look like what you started with. So in this way, you can actually pre-design the focus that you want, and then I will have a way to create such a focus. And of course, the system you see from the previous slides is kind of a big, but nowadays, if you pay attention, there's developments in so-called meta surfaces and meta lenses. You actually can fabricate those with a compact device and just sticking to your optical path, you will be able to create those kind of patterns. So, of course, a very long skinny needle is not surprising, but you can create other things, for example, very long needles or pipes, or a spherical XYZ same size, or a bubble. Or you can have a chain in much more complicated patterns. This is actually one demonstration show how complicated it can be. This is so-called a Mobius stripes. So this is actually the focus spot. Then you draw a line. Say this is actually a heart shape path. Okay, you tell me this is the path you want. And you want to control the polarization along this path so that you start from one point and the polarization start to continue to rotate around this path. After one round trip, it will point to the opposite direction. So this is actually the polarization map of along this path, and actually we can create this. And almost arbitrary path trajectory you designed, we can create this kind of a distribution for you. So here's another example, because yesterday we went to this HISO, they were doing the CD measurements. Basically, you have this radiation coming to the sample, and you hit certain magnetic metal surfaces. And then you look at left-hand and right-hand spins, you see different scattering, and you can have result of your materials. And this is something similar, actually. This is a light. This is basically the illumination pattern, but illumination, you can see that we're continually changing the internal polarization structure of it. And that's the corresponding focus. So for one moment, you see that when you have a dark line in the center here, I cannot stop it. You will notice that when you have a dark line in the center, the top half and lower half has a different color of the circles. One is green, another is blue. And that means the handedness of spin is opposite. So the top is the left hand, the bottom is the right hand. But they're ideally symmetric. Under that condition, if you look at the focus is almost still diffraction limited. But the polarization state within that focus is very strange. Well, if you look at the XY plane, so the light propagated along Z direction. If you look at the XY plane, the polarization is linear, which is what we expected. You have left-hand spin, right-hand spin, they're symmetric. And when you focus it, of course, they're going to cancel each other, give you a linear polarization, right? But at that moment, at the same time, if you look at XZ plane, the polarization is circle. So that means that I have a spin, but the spin direction is along Y direction. Your light propagate along Z, but spin is transverse to it. And that's so-called transverse spin. Basically, you can synthesize a spin state by playing with this polarization structure of the illumination. And you might ask, what's the use of it? So this is actually something related to what we see yesterday of this CD things. So imagine you have a waveguide. This is the silicon nitride waveguide. Then you have like a dipole or quantum dots sitting on top of the waveguide. And then I use light to excite it. And of course, the dipole going to radiate light. Then I ask you, well, what's the percentage of light going to go left? What's the percentage of light going to go right? You're probably going to tell me it should be equal amount, right? 50 left and 50 right. But if you use this transverse spin state to excite it, for example, the light is actually coming from the top. If you use the spin pointing up, you will see that light actually all goes to the left. If I switch the spin state to pointing down, you will see the light go on to the right. It's like you have a virtual valve you can turn on and off, but actually you're controlling it with the spin state of light. And also, this is actually another example. If you have a cross the waveguides, and again, you put quantum dots in the center, you can control continuously what's the percentage of the radiation goes left or top. It's just like you can change the coupling ratio between these two waveguides, but all by playing with the spin states of light. But this is spin states called transverse spin, as opposed to the normal spin states that we're familiar with. Okay, so then we start to ask more complete questions. If you have a complex medium, for example, like turbulence or underwater environment or skin, it's highly scattering, lossy medium or multimodal fiber. And we would like to achieve something. For example, I want to efficiently transfer information from here to 10 kilometers away. Or I want to focus my light, 1 millimeter under my skin. The question is, what is the illumination should look like? I guess at that time, when we posed this question many years ago, we don't know an answer. So we put a bunch of question mark here. But we know one thing, the illumination is not going to be a Gaussian beam. It's not going to be plane wave. So what we did, actually, we did a trial thing where we look at different situations for like a Gaussian beam, a vortex beam, and these vector beams propagates through the same turbulence. And we find out actually the vector beams will propagate longer in turbulence, about twice longer the distances of a regular Gaussian beams. So that's the, we did not do experiment, but later actually the Boyd's group and some other group in South Florida did experiment to verify that. This is a recent work we did. So this is actually to illustrate that if you have the capability to structuralize in space, what strange things might happen. So this is actually the light coming down. This is spatial light modulator. And we focus through, in the middle is actually a ground glass. That's a scattering medium. Now, if you focus light to ground glass, you know you're going to have a speckle patterns, right? It's going to be random. But what we want to do is to pre-compensate that randomness of the scattering glass so that we still can produce a nice focus spot after that. And indeed, we were able to do that. This is actually experiment results. And you can see on the 6D camera, we can form a nearly diffraction limited focus spot, and then you can do scanning of it. Sometimes the composition is not very well. You see some fluctuations in the background. But the answer is by playing this spatially structured light, you can overcome some of the very complicated scattering media phenomena. I don't have the result here. We just have a recent paper accepted by Optica. that shows that you can do similar things through multimode fiber. So if you have a multiple fiber and you inject light in it, you have lots of different modes. And on the other side, you're going to have, again, speckle patterns. But if you do things correct at the beginning, you actually can overcome these phenomena, those so-called multipath problems. On the other side of the multimode fibers, you have like a single mode behavior. So that's a result is going to come out fairly soon. So that's basically what we did in the past in terms of structuring light in space. And the question is now, can we combine space and time together? If you do those at the same time, what new thing might happen? So we start to pursue this in about 4 or 5 years ago, since I returned to China. It turns out it's very simple. We just need a very simple device. A simple device is called pulse shaper. And that's actually something you can buy from the market very easily. And the principle is very like this. So you have a pulse light coming in, and you have a grating. A grating basically separates the different color of the pulse into different location in the Fourier plane, right? This is a cylindrical lens. Now, in the Fourier plane, if you have those different frequency components or different omega, and you can put a mask here. You can, for example, I can block some of the wavelengths, but let other wavelengths go through, or more sophisticatedly, you can modulate different components, right? And then you go through basically a symmetrical system. It's a 4F system. You symmetrically have another cylindrical lens here, another grating here. And again, it goes back to the time domain. And all of a sudden you find out, well, if I have input pulse look like this, my output pulse will have a different shape. That's called pulse shaper.
Can you build your mask as a hologram?
Yes,
Hologram for the mask?
of course. But that's actually basically what we did. So this is actually people are familiar with for a long time. But the thing is, in the past, so this mask in the middle is always one-dimensional. It's a grating. So because they want, this is the temporal, and a Fourier transform here is omega, right? And then they say, well, I only care about omega, so I'm going to have a one-dimensional linear grating to select a certain component to block other components, and then I have a different waveform. But this plane is naturally two-dimensional thing. So why not put another information on the other dimension, which is a space? So that's exactly what we did. Here's actually our first experiment. So even this is our fiber laser. We built our own fiber laser, produced femtosecond output. And then when it come out, we build our own pulse shaper. So this is the grating. This is cylindrical lens. That's reflection type of spatial light modulator, but it's two-dimensional. It's like a little TV. It's a reflection type, so it's again, so the light hitting here goes here and hitting the spatial light modulator, then become modulated and going back. So just like the 4F system I showed you previously, but this is reflection configuration. And then, okay, we build this. We don't know what's going to happen actually. So first thing we tried is we're going to put a vertex face, which is this is the helical face on top of this, and see what happens. But since this is the pulse, is the femtosecond pulses, we need to be able to measure this pulse, right? So what we did, we built a very simple system. It's an interferometer. So basically, we take the same pulse, and these two gratings actually compress the pulse to shorter duration. And then it goes through a delay line. So basically what happens, this reference pulse going to interfere with my signal pulse. On the 60 camera, you're going to see this interference fringes. That's just interferometer, right? But then we change the delay line. You select a different part of the pulses. Essentially, it's like chopping an onion. If you have an onion, you have different layers inside of it, right? That's my pulse. But just looking at onion itself, you don't know what's inside of the pulse. And you need to have a tool to look at it. And the tool is this reference. This reference is like a sharp knife. You take the knife, you chop it on into different slices, you look at the cross-section, and then you reconstruct the three-dimensional structure of the pulse. And indeed, you find out that we have a pulse flying in time, but this pulse has internal structure. It has a hole. You see this hole there? And that hole is caused by the phase structure of that pulse in space and time domain. And that phase structure has a singularity points. So that's a helical phase. Now, if you work out the mass, you will find out, just like we had in the spatial domain, if you have a helical phase, it's going to have a quantity called orbital angular momentum states. But this orbital angular momentum states is, again, transverse to propagation direction, as opposed to normally the OEM is along the same direction. So this is the so-called transverse OEM of the light.
Can you create multiple charge?
Oh, yes. I don't have the slides, but it turns out the thing is very interesting. There's a lot of interest of this after with this, is that this technique is so simple. Essentially, what you need to do is to change the pattern on the spatial light modulator. If you want a topological charge of 3, I change this phase pattern to topological 3. Or if you want to have a bunch of those in space and time, we can create a lattice of this by display, an array of a vertex pattern on it. And this is actually another thing we did later. So because we have this space-time vertexes, the very nature thing is that we have spent 20 years on the spatial structure of light. What if I just put another spatial modulation after this? So that's what we did immediately. This is a space and time vertexes, you can see, but I just put another spatial light modulator after that and putting another normal vertexes on it. So all of a sudden now you have a pulse, you have one transverse terminal, the space-time vertex, and then you have a longitudinal terminal, which is the spatial vertexes. Now, I think yesterday when we talked about Hawkins, when you want to map to Hawkins, you need two types of singularities. And that's essentially what allow us to build the Hawkins, because here we have one singularity in the space and time, another singularity is in space. And by combining these two together, we will be able to build Hawkins. This is just the previous one. This is the result of a simulation. What's interesting is you see these two vertexes actually are interacting with each other. So the space and time is twisting the space, and the space actually also twisting space and time. This is experiment results. I guess you can show that the tunnels of this vortex core is being twisted. We have other results is that if you focus this very tightly, this twisting phenomena becomes much more complicated. You're going to have this so-called vortex splitting and recombination in the focal volume. And of course, you can do other type of things. Like I said, the cylindrical vector polarization is actually also has a singularity, but that singularity is different. It's a polarization singularity. We can do that easily with our setup, or we can create a wave packet or pulse. You can see there's a hole here, that's a space and time. And there's another hole, that's the polarization singularity. And if you kind of cut, you can see that two tunnels. But the difference is here, they don't interact with each other. They don't twist each other because there are different type of singularities. Again, this is in the practical situations. When you focus it, since it's much more complicated, you can create all kinds of very complicated vertex structures. Okay, so we try to make things more complicated because you have more control. So this is actually the pulse shaper. And what did is very simple thing in this setup here. We just put a quarter wave plate in there. But the quarter wave plate is at 45-degree orientation. Now, once you did this, everything else is the same. The funny thing is, this quarter wave plate will allow us to control the polarization in space and time. So what happens is this. So anything here on the spatial line modulator, of course, the phase modulation. With the quarter wave plate with such orientation, what happens is if you put a zero phase on this SLAM, nothing happens, of course. But if you put a pi phase on it, what happens is that the light coming here and return, the polarization will be rotated by 90 degrees. So in other words, we can use the phase pattern here to control the polarization pattern in space and time. And this is just one example. I put a very simple grading pattern on it, 0 pi phase pattern. And when the pulse coming out, of course, it's still a pulse. But if you analyze what happens within the pulse, you will see that the pulse has the polarization very quickly changing in time. So the red is X polarized, the blue is Y polarized. You can see that X and Y polarization are switching every 100th of a second. So by doing the very simple modulation on the spatial light modulator. And if I use a checkerboard pattern, then I have a very complicated thing. This is actually the thing I want to discuss with Evan and Boris. Is this related to time crystal? This is something that we have been looking to, but we are not 100% sure about the concept of time crystal yet. But we can produce a space-time lattice of light with different properties. So this is the quasi-periodic structures in space and time. And if I just put a vertex face on it, what's happening is the wave packet is going to have a very complicated polarization structure, as you can see, something related to what you showed a moment ago in the liquid crystal. But this is actually the polarization of the light in space and time. You can see it's changing with a very interesting topology. If you can do polarization modulation, of course, you can do amplitude modulation in space and time as well. You just need to put linear polarizer to filter out the orthogonal components. So you can write in space and time. And this is actually the logo of our university, USST, but it's in space and time. It's not in the space itself. And another thing we tried recently is through this space and time wave packets. People are still studying its properties and how to propagate, etc. We show that you actually can propagate these structures and topologies through optical fiber as well. And this is appeared as a cover of Advanced Photonics. Now, let's get back to the things we start with. Can we produce a toroidal vortex with light? The answer is yes. Once we produce this guy here, we know immediately we can do that now. So what we need to do is actually, this is spatiotemporal vortex. And you can use two cylindrical lenses to amplify or magnify one direction. So basically making it longer, like a pipe. But you still have the vortexes in this pipe. Then the key component is this guy here. It's called a conformal mapper. Like I mentioned, when we started OEM communications, we need a device called a conformal mapper to do that. What a conformal mapper does, I think I have, yes, this guy over here. This is basically illustrate what this device is doing. Okay, so this is actually, I use my cell phone to take a picture. This dark line here is my computer screen. And you can see that this device is actually bending this edge of the screen. Now, if you do the bending just right, you see that edge, straight line of edge become a circle, right? So that's what the conformal mapping is doing. You take this long line here, this pipe here, and it does the conformal mapping. It's a wrap around. And if you control the wrapping correctly, the two ends of that pipe are going to meet each other, form a ring. But it preserves this vortex inside of this cross-section. Now you have a ring structure, but you have internal vertices going around. That's exactly what a toroidal vortex is. And so we can actually measure this structures. You can see the ring structures, and at different locations you can construct a face. Indeed, you have this face structure as well.
So it's a typical size of the experiment, few millimeters.
This is about 3 millimeters in diameter. Yes.
The temporal direction is like few picoseconds.
That's about 2 picoseconds, yes. But it can be compressed or stretched. So that was shown as a cover of Nature Photonics and received a lot of attention. But then the next thing is what we can do upon this. So you can see that by doing this wrapping or conformal mapping, we're forming a toroidal singularity. But in order to build a Hopfians, you need two types of singularities. One is this toroidal singularity. Another is that straight line here. That's every circle is going around it. So this is actually another singularity you need to build. It's very easy for us. You just need another spatial light modulator to put a vertex on it. And then you will be able to create a toroidal, the Hopfian structures. So this is just something I actually already seen from talks yesterday. So this is in liquids, and people can create, all kinds of interesting things with this. That's the knotted water we talked about last night, right? But optical-wise, you can do similar things by using combinations of different single vertexes, and you kind of nest them together. You can have this very complicated continuous wave knotted structure of this vortex core, but this is using continuous waves. But for us, with this toroidal vortex that we created, we just put in another face on it. You look at the equal face lines, you will see this very complicated nested links, and that's exactly what the Hopfian is about. So that's the Hopfian structure we created and published last year. And such a structure or setup allow us to do a lot of different things. For example, you can put a different topological charge in the toroidal vertex or the spatial vertex. Then you can create lots of interesting structures. But the bad news for us now, or the challenging for us now, is how to measure this. We can create it in an experiment, well, we think we can, because what we only need to do is to change the phase pattern of spatial light modulator. But we don't know how to measure those complicated structures because it's just too complicated right now. So we're looking to the possible different ways of characterizing these structures and even more complicated ones. This is actually Mark Daniels' work I also mentioned yesterday. So hopefully, as a result, you can see that with these multiple parameter control nowadays in space and space-time, we are able to produce lots of complicated topological structures in light. But again, if you ask me what's the applications, my answer right now is still I don't know. But hopefully in the future, next years also through collaboration with WPI and also the affiliate members, we'll be able to find out the applications of those interesting topological states. So this is actually my lab in Shanghai. We call it Cosmos. It's actually two parts, the complex optical fields and the meta optical structures. So the theme align with this WPI very well. Of course, we mostly in optics, but hopefully we can find synergy among us. And that's actually essentially what we do. We do light structuring. We also produce nanostructures with different topology. And hopefully we can combine them together and find something new. This is something I start to use a lot nowadays because I don't know the application of these things. So I just saying, well, we probably are providing a solution that's looking for problems. That if you have problem, you think that the structuring light in space and time may be able to help you. You're welcome to discuss this matters. Just one example, actually, I think you mentioned BEC yesterday, right? People try to, answer whether the universe is going to be continually expanding or is actually someday it's going to shrink back. So people did this simulations in BEC to show, whether it's going to expand or not, but I'm not 100% sure the answer. But I think we also can use our light to produce initial states. If you want to do some simulations how this works, we can provide excitation for you. So the excitation source as an initial point. Then you can study what happens afterwards. So again, this is acknowledgement of funding agencies and my group. Thank you very much.